Okay. So I'm from a place called the Joint Quantum Institute, which is joint between the University of Maryland and NIST. And I'm part of NIST's Laser Cooling and Trapping Group. And I just want to mention my colleagues, the permanent members of the Laser Cooling and Trapping Group, Gretchen Campbell, Paulette, Trey Porto, and Ian Spillman, with whom I'm privileged to work on a daily basis. Okay, the future of time. Well, why is it time? Oops, wrong way. Why is it time? Why is it time to think about time? And the answer is, as you've heard, because time is the foundation of our measurement system. And that system is in revolution, as you heard in the introduction. Because as of the 20th of May, which I'm sure you all know is World Metrology Day, the decision that was made in November will come into effect. And it will be the greatest revolution in measurement since the French Revolution. The French Revolution brought us the metric system. And today, the official name of that metric system is the International System of Units, the Système International d'Unité, or the SI. So when you hear me say SI, that's what I mean. I'm talking about the metric system. And the metric system is undergoing a revolution. And the nature of that revolution is that every one of the base units of the SI, the kilogram, the meter, the second, the ampere, the kelvin, the mole, and the candela, every one of those base units is going to be defined by defining a fixed value for some fundamental constant of nature. Now, we're going to have a symposium later this morning in this very room after the coffee break, in which you're going to hear some of the details of how that change is going to take place. And I really encourage you to come to that. But before that, I want to give you a little bit of a feeling for how it's possible to define one of the units of measurement by fixing the value of a fundamental constant. And I'm going to do that by, with apologies to Stephen Hawking and his wonderful book, A Brief History of Time, I'm going to bring you a short history of length. And the reason is that length is already defined. The unit of length, the meter, is already defined by defining a fundamental constant of nature. So let's see how that works. Let's begin by thinking about the way the ancient people defined length. They used the human body as the standard of measurement. Now, this was wonderful. A yard was the distance between your nose and the end of your fingertips. A fathom was the spread of your arms. A cubit was the distance between your elbow and your fingertip. And of course, a foot was a foot. Now, this was really convenient because you always had your measurement standards with you. On the other hand, it wasn't very consistent. If you were buying fabric from a short fabric merchant, you might not get as much fabric as you had thought you would get when he measured it out using his arm. And so over time, people developed better ways of doing this. They developed artifact standards, a rod made out of stone or a rod made out of metal. And these rods, these artifact standards became the standards of measurement for a city or for a country. And eventually, after the famous 1875 Treaty of the Meter, the Convention de Mètre, this standard, this platinum iridium bar with 2 scratches on it, became the standard of length for the entire world. The meter was defined for the entire world as being the distance between these 2 scratches on a meter bar that's kept in a vault at the BIPM just outside of Paris. Now, this was wonderful. It meant that everyone in the world agreed upon what a meter meant. But the problem was that it soon became evident that it wasn't so easy to tell what the distance between 2 scratches was, because after all, they're scratches. And when you look at them with a traveling microscope, you have to decide where is the middle of the scratch. And you can't do that as well as people had begun to be able to measure length using light and using interferometry. So an interferometer like this is a Michelson interferometer. You have light say from a lamp come in here, it's split. Some of it goes to this movable mirror, some goes to a fixed mirror. And as you change the distance, the position of this movable mirror by 1/2 of a wavelength of light, a fraction of a micron, a fraction of a millionth of a meter, this interference pattern that you see here goes from being dark to light back to dark again just by changing the distance by a fraction of a micron. So that means that using light, people were able to make measurements much better than they were able to realize the definition of the meter using the meter bar. And so that meant that something had to change, and it did. In 1960, sort of interestingly, the year that the laser was invented, the definition of the meter was changed from being the distance between two scratches on a platinum iridium rod to being a certain number of wavelengths of a krypton lamp, which is pictured here. Well, that was great. We now had a consistent definition. People had been using the wavelength of light as a kind of de facto definition. Now we had the real definition of length being based on the wavelength of light. But soon, people found out that the purity of the light from that krypton lamp was not sufficient for the kinds of measurements that they were now making using lasers. Remember, 1960 was the year the laser was invented. And soon there were lasers that were so good that the purity of the light coming out of those lasers was significantly better than the purity of the light coming from a krypton lamp. And so by the 1970s, people were using helium, iodine-stabilized helium neon lasers. You would tune the red light from a helium neon laser to an absorption line in the iodine molecule, and that became the new de facto standard of length. And everybody was reporting their lengths in terms of this not exactly legal, but much better standard of length. And so it became clear that once again, we needed to change the definition of length. Now, the obvious choice would have been to redefine the meter to be a certain number of wavelengths of the light from an iodine-stabilized helium neon laser. This would have been completely in line with the historical spirit of changing definitions in accord with improved technology and metrology. So just as we changed from the distance between two scratches on a metal rod to the wavelength of light, it would have made sense to change from the wavelength of light from a lamp to the wavelength of light from a laser. And the obvious definition would have been to say a certain number of wavelengths of the iodine-stabilized helium neon laser. But fortunately, the people of that time did not make the obvious choice. They made instead a brilliant choice. They defined the speed of light. In 1983, the International Conference on Weights and Measures made the decision that the meter is the length of path that light travels in vacuum during this time interval. And what that means is they've defined the speed of light. Now, think about this. If you've defined the speed of light and you can measure the frequency of light, and that was an important feature, to be able to measure the frequency of light, then that means, because of this relationship, which always holds, that the wavelength times the frequency is equal to the speed of light. If you measure the frequency and you've defined the speed of light, you know the wavelength. For any light that you care to use, if you can measure its frequency, you automatically have a perfect ruler. And better than that, if the technology of lasers becomes better, if the technology for measuring frequency becomes better, all of that improvement in the technology is automatically incorporated into the definition. We don't need a new definition every time a new laser comes along that is so much better than all the previous lasers. And we don't need a new definition when a new technology for measuring the frequency comes along. And at this time, in 1983, the technology for measuring the frequency was not all that wonderful. It took a big room full of equipment to measure the frequency. But these guys, Jan Hall and Ted Hensch, developed a new method for measuring the frequency of light called a frequency comb, which I'm not going to tell you about, but it's beautiful. And they got the Nobel Prize for that in 2005. People had been using their new technology for measuring frequency and for making lasers that were more pure in their light, more coherent in the light that was coming out of them, that had been used for years to realize the definition of the meter already. So that new technology was already part of the old definition of the meter. In that same year, 2005, Roy Glauber got the Nobel Prize for his quantum description of the coherence of light, which is an important feature in making this kind of light into a good standard for length. Sadly, Roy passed away at the end of last year, and he's sorely missed. Okay, the definition of the meter is, in my opinion, both brilliant and beautiful. This feature that it incorporates all possible new technologies is a really wonderful thing. And unless we dramatically change the way in which we measure length in the future, there should never be any need to change the definition of the meter again. This should be the last redefinition of the meter. In a sense, we're realizing in this definition the ideal of the French Revolution that led to the metric system of units that will be for all time and for all people. On the 20th of May of this year, that same beauty and brilliance is going to be brought officially to the definitions of the kilogram and the ampere, the kelvin, and the mole, and that's in that SI symposium that is going to follow this plenary session after the coffee break. Well, as I mentioned, the SI is really being tied into a wonderful package where all of the base units of the SI are being defined by defining constants of nature. And this really does realize this dream that was part of the French Revolution in measurement to provide units à tous les temps, à tous les peuples, for all times, for all peoples. But what about time itself? As you heard in the introduction, we haven't had a redefinition of time. What about the second? Well, what is the second? Well, since we've had seconds, the second has been 1 day divided by 24 hours per day, divided by 60 minutes per hour, divided by 60 seconds per minute. So the second is 1 day divided by 86,400. But what is a day? Well, it's obvious. It's the time it takes the sun to rotate on its axis. It turns out you have to define it to be the solar day as opposed to the sidereal day, but still, that seems like a good definition. The trouble is that since around the year 1900, we have known that the rotation of the Earth is not constant. Now, actually, philosophically, that presents a problem because the second is defined in terms of the rotation of the Earth. So by definition, the rotation of the Earth is always constant. But we could make, by 1900, we could make clocks, as it turned out, mechanical clocks, pendulum clocks, that were better, more stable than the rotation of the Earth. And while, in a sense, officially, the rotation of the Earth was always the same number of seconds, we all knew that it wasn't, because we had these better clocks that could show that the rotation of the Earth wasn't constant. And by the middle of the 20th century, there were other kinds of clocks, atomic clocks. This clock right here used an ammonium molecule as its standard of ticking. Now, one of the great things is that the Earth may change its rotation rate. Why? Because of things like the tides that slow down the Earth. If ocean currents change, it changes the angular momentum of the water, and the Earth has to compensate in order to conserve angular momentum. If there's an earthquake and it redistributes the mass so that the moment of inertia changes, that will change the rotation rate of the Earth. All these things change. But as far as we know, atoms and molecules do not change. And so having a molecule as the standard of time was the idea behind this clock in 1949. In a sense, this was the first atomic clock. But of course, it wasn't an atomic clock. It was a molecular clock. But it was the same idea. A few years later, at the UK National Metrology Institute, the National Physical Laboratory, Perry and Essen made a cesium clock in 1955. and that cesium clock could also keep time better than the Earth. And so, by the middle of the 20th century, we had the situation that Earth rotation metrology was insufficient for the needs of time metrology, and atomic timekeeping, which was clearly a better technology and over a decade old. That was the situation in 1960. And in 1960, the International Conference on Weights and Measures defined the second to be a fraction of the tropical year 1900. What were they thinking? Atomic clocks have been around for more than 10 years, and they defined the second to be a fraction of the year 1900. Well, you have to admit, the year 1900 doesn't change. But it's not so easy to measure today or even in 1960. So finally, they came to their senses. And in the period of 1967 to 68, that international body adopted an atomic definition of time, which we still use today. The second is the duration of 9,192,631,770 periods of oscillation of the radiation that corresponds to the hyperfine separation in the ground state of cesium. That's the current definition of the second. So why are we worried? It's a wonderful definition. It's based on something that is, we presume, a constant of nature. Well, let me just say a little bit about how such clocks work. And this is common to all atomic clocks. For cesium, we imagine that we have an atom with a nucleus, which is a spin pointing one way, a valence electron with a spin pointing in some direction. And if the orientation of this spin changes relative to the nucleus, then that changes the energy of the atom. Now, I'm lying a little bit here. And those of you who are good atomic physicists know that I'm lying, and you're going to forgive me for the lies that I'm telling about the triplet and singlet states of cesium. But that's, so among friends, let's just say that the electron flips relative to the nucleus. Okay, and in order to make that happen, in order to make that happen, what you do is you shine in microwaves at the right frequency, and when it's exactly the right frequency, then it makes the electron flip, and if it's not the right frequency, it doesn't, and you can tell whether the electron flipped or not, and in that way, you just adjust your microwaves until it makes the electron flip, and then you know that your microwaves have that frequency. Now, in fact, it's a lot more complicated than that, but that's the basic idea behind an atomic clock. And that has worked well with all sorts of wonderful tricks. And since the time of Perry and Essen in 1955, well, this point is from 1960, the quality of these atomic clocks has improved exponentially with time. You can see this is a logarithmic scale. So this represents an exponential increase in the quality of these clocks over time. And the reason why that has been possible is because people in national laboratories like the PTB, like the National Institute of Standards and Technology, have been working really hard trying to make these clocks better and better. This is a picture of the clock room at the PTB, where there's a whole array of cesium clocks, and work in laboratories like the PTB, like NIST, like the NPL, and other laboratories all over the world has pushed the technology to the point that these clocks have gotten to be about an accuracy of about 1 part in 10 to the 14. That's an almost unimaginable accuracy, a part in 10 to the 14. But these clocks aren't getting a lot better than a part in 10 to the 14th. Why? Why aren't they getting a lot better than a part in 10 to the 14th? Because the atoms are moving. The way in which an atomic clock works, and here's a picture of one of the last atomic clocks of this design at NIST, is at one end of the thing there's a can that has some sodium metal. You heat it up, you vaporize the cesium. The atoms come out of the oven and go down this tube at a velocity over 100 meters per second. That means it takes a few milliseconds to get from one end to the other. And that short period of time, that few milliseconds, means that the line width, just the Fourier transform limited line width, because you've got a finite observation time, you have a certain line width, and that line width is on the order of 100 hertz. And 100 hertz out of 10 to the 10th hertz is not so small a number. That's 10 to the minus 8. And these things want to be 10 to the minus 14. That means you have to split the line to a part in a million. And that's not so easy. But these people are heroes, and they do it. But doing better is difficult. Why? Well, there are Doppler shifts. The Doppler shift changes the frequency of the apparent frequency of the cesium atoms by a fractional amount equal to the velocity divided by the speed of light. This is a few parts in 10 to the 7th when you want to do a part in 10 to the 14. That's a disaster. But these guys are really smart, and they come up with all kinds of tricks to reduce that Doppler effect. And the degree to which those tricks don't work perfectly is the thing that limits these clocks at about a part in 10 to the 14. And then there is Einstein's time dilation. These atoms are moving clocks. And that means, as Einstein taught us in 1905, that moving clocks run slow. And the degree to which they run slow is something that there are no tricks to fix. You have to measure the velocity of the atoms and correct for it. And the degree to which you can do that limits these clocks to about a part in 10 to the 14. So we have these clocks, and you might say, well, why are you worried? A part in 10 to the 14, that's wonderful. We are the National Institute of Standards and Technology. We are not satisfied with a part in 10 to the 14, and neither is the PTB. We want to do better. How are we going to do better? We're going to make the atoms move more slowly. The answer is laser cooling. Now, I could give a whole 1-hour lecture on laser cooling, and some of you have heard me give a 1-hour lecture on laser cooling, but I'm not going to do that today. Suffice it to say, by pushing on atoms with the radiation pressure from light, you can make the atoms slow down, and you can make their spread of velocities incredibly low, so that it's possible to cool cesium atoms down below a temperature of 1 microkelvin. At 1 microkelvin, their velocities are less than 1 centimeter per second. So instead of more than 100 meters per second, they're less than 1 centimeter per second. And cesium fountain clocks like this, you see, there's Don Meekhoff and Steve Jeffords, and they cool cesium atoms down here, and they toss them up in the vacuum, and they fall back down. And you see, the wonderful thing about it is, if you throw something up about 1 meter, it comes down after about 1 second. So instead of a few milliseconds to make the measurement, you have a full second to make the measurement. And the velocities are so much smaller than the velocities in the old clocks that these clocks have eventually gotten so good that they're realizing the second to an accuracy of about a part in 10 to the 16. So here, by virtue of laser cooling, this exponential improvement in clocks has continued down so that at the present time we're at about a part in 10 to the 16. So this is a kind of Moore's law for clocks. It just keeps getting better and better. But the problem here is that now at a part in 10 to the 16, we are facing a lot of problems again. And what are those problems? Lots of little things. Black body radiation, just the thermal radiation from the fact that you're in a room at room temperature shifts the frequency of the cesium clock, and you have to calculate that and make sure that the temperature is uniform, and that makes it difficult and hard to do better than a part in 10 to the 16. Collisional shifts, something we never worried about in the atomic beams. At very low temperatures, the collisions that the cesium atoms have, even at incredibly low densities, the densities are so low that most people would call it a good vacuum. But with 10 to the 6 cesium atoms per cubic centimeter, that's plenty to make an atomic clock. But those atoms collide with each other, and they shift the clock frequency. And then we have the gravity-limited observation time. So I said with great pride that when we throw something up a meter, it comes back down after a second. If I want to make that longer, let's say I want to improve by an order of magnitude, I have to throw it 100 times higher. And that's simply not practical. In this room, I can't even do it. So the gravity-limited observation time imposes a constant line width on the atoms that, it sounds like this, maybe it's just that I'm stuffing this thing in my pocket, but it sounds like the microphone isn't as good. Is it still okay in the back? Good, okay, okay, good. Well, let me move this a little closer. Okay, so we have all these little things that produce shifts, collisional shifts, black body shifts, that is light shifts, gravity-limited line widths that are essentially a constant. If we could make the frequency higher, then that means that fractionally these things would be smaller. So if we decide that we want to go to frequencies higher than the 9.2 gigahertz that cesium gives us, if we go to optical frequencies on the order of 10 to the 15 hertz, then all of these effects are going to be fractionally smaller by that ratio of the optical frequency to the microwave frequency, which is a pretty big number. And so what we're doing now is developing optical frequency standards. And we're very fortunate that nature has given us some wonderful optical clock transitions. Here's one example. Strontium-87 is a favorite atom, and it's got wonderful transitions to do laser cooling to get us down to hundreds of microkelvin, and then another transition to get us down to a few microkelvin, and then a clock transition operating at a frequency of about 4 times 10 to the 14 hertz with 1 millihertz of natural line width. That means if you see the line at all, you're already at parts in 10 to the 17, just seeing the line, if you can have this kind of natural width. So this is wonderful. And the thing that, there's a lot of things that had to happen in order to make this possible. A lot of new technologies, a lot of new metrological improvements. Well, one of them was laser cooling. It fixes the motional shifts as we've seen, but it does something else. It allows you to trap the atoms using light so that they stay around for essentially as long as you want. And that means that you no longer have this limited time for observation, limited by gravity in an atomic fountain. It's essentially not limited. So laser cooling allows that. And then the technique for trapping the atoms with light. And now we have to worry about the fact that imposing the light on the atoms changes their frequencies. And so a wonderful idea to choose the wavelength of the light so it shifts the ground state the same amount that it shifts the excited state. These are called magic wavelengths, and that allows us to have long observation times without light shifts. Now you notice that I've put "without" in quotation marks. That's because it's not really true. But let's just say among us friends for the moment that we can trap the atoms without shifts. The fact that we can't is one of the things that limits the performance of these optical frequency standards. It required new kinds of lasers, new stabilization methods that allowed lasers to have line widths, excuse me, that are comparable to the line width of the atom. So it's now, I find this mind-boggling, because when I started using lasers, they had line widths of 1 megahertz. And today, Junyi makes lasers that have line widths of a few millihertz. This is just astounding how this has changed, and it's been due to the work of people like Jan Hall and Ted Hensch and their colleagues and the people who have come after them. And this was an important part of what has made optical frequency standards possible. Now, I mentioned this before, optical frequency measurements and frequency combs. And the asterisk is just to remind myself that I'm not going to talk about optical frequency combs, but they're wonderful. It gives you a whole set of frequencies where if you know one of them by locking it, say, to an optical transition in an atom, then you know all the other frequencies perfectly, and this is just amazing. Okay, so this has created a tremendous revolution in timekeeping. So here was the old exponential improvement of microwave clocks. Optical clocks had a different exponential, a much faster exponential, and around the end of the years 2000, these optical clocks became better than the best of the microwave clocks and have been improving ever since. How good are they? Well, in Junyi's laboratory at NIST in Boulder, Colorado, he has strontium atoms operating with an accuracy of 2 × 10⁻18. Now, first of all, how can that be? He can't have an accuracy of 2 × 10⁻18 because we don't know what the second is to better than about a part in 10 to the 16. So when I say an accuracy of 2 × 10⁻18, what I mean is he can lock a laser to the center of the line in strontium to an accuracy of 2 × 10⁻18. But that is not related to what the second is. You see where this is going, right? It's an old story. Dave Wineland, one of the inventors of the idea of laser cooling. Laser cooling was invented in 1975. Wineland and Daymelt were one group that invented it. Another group was Hensch, Ted Hensch, who also did the frequency combs, and Art Shallow, one of the inventors of the laser, came up with the idea of the laser cooling. These 4 guys, Shallow and Hensch and Wineland and Daymelt, in 1975 invented the idea of laser cooling, which revolutionized clocks of all kinds. Every one of those people eventually got a Nobel Prize for something else. Okay, so Dave Wineland and his group have achieved with aluminum ions, a single aluminum ion, in fact, a single trapped aluminum ion, and using quantum logic readout. Remember the talk we had yesterday about quantum logic? That's what was used to achieve this accuracy of 9.5 × 10⁻19, the first time that the accuracy of a clock had reached the parts in 10 to the 19. Absolutely astounding. Now let me make an aside about having clocks that are that good. If I have some emitter that is emitting radiation, and it's sitting in a gravitational field, like the gravitational field of the Earth that has some acceleration of gravity, 9.8 meters per second squared, and I shine that light up, as the photon climbs in the gravitational field, its potential energy increases. I think of the photon as having a certain mass associated with Einstein's famous equation E = mc squared. So I ascribe a mass to the photon of E divided by c squared, and that mass has to acquire potential energy as it rises in the gravitational field. That means the photon energy has to decrease because it's got more potential energy, so its energy of oscillation has to decrease, so there should be a lower frequency. So as the photon climbs in the gravitational field, it should have a lower frequency. And I can calculate what that is just using classical physics, and I find that it's a part in 10 to the 16th per meter. That means if I have an optical clock that is good to a part in 10 to the 18, for that to be meaningful, I have to know where that clock is in altitude to a centimeter. Now that's a real problem. But another way of looking at it is, it's an opportunity. It's an opportunity to use clocks to measure where you are in the gravitational potential. And here's a paper from NIST in Boulder, where Andrew Ludlow and his colleagues are describing an ytterbium atom clock, so different from strontium, a great atom that has an accuracy of 1.4 × 10 to the -18, but an ultimate stability of 3 × 10 to the -19. So that's 3 millimeters. And they're advertising this as something, oh, and 2 different clocks that are the same to 7 parts in 10 to the 19. And they're advertising this as a clock that can perform geodesy below the centimeter level. And I want to emphasize, this is an international team, not just the US, China, Denmark, Italy, South Korea, the United Kingdom. Junyi doing an optical clock comparison with an accuracy of 6 × 10 to the -19 in just 1 hour of averaging. This is just astounding how wonderful this is. And I can't resist pointing out that one of the authors of this, Uwe Stier from the PTB, because this was a collaboration between NIST and the PTB and a German company that makes optical frequency combs. Uwe Stier is an alumnus of the NIST laser cooling and trapping group, and we're very proud of that. So the future of optical frequency standards keeps getting better and better, and this slide that I borrowed from Junyi is saying, look, this is just going to get better and better. We're going to go into the 10 to the minus 20ths. So this has been an international effort, and one of the great heroes of this international effort is Fritz Riehle of the PTB. We have an expression in English when someone is really dominant in a field, we say they wrote the book about it. Well, Fritz literally wrote the book about frequency standards, the realization of the second. At PTB, lots of different optical clocks are being developed, both trapped ions and optical lattice neutral atom clocks. Again, taking advantage of this idea of the gravity dependence of these clocks has allowed them to take a transportable clock and move it around in the Alps and measure the gravitational potential using this transportable clock. Transportable ion clocks using ytterbium ion clocks for tests of some of the most fundamental symmetries of nature, things that everyone is believing is going to be a fundamental symmetry of nature, but maybe isn't. And now we have the ability to test this at levels that were never possible before. Just amazing things happening. And it's all because of this worldwide international effort to make optical frequency standards better and better. And now we are again at a crossroads where we have to decide what to do about the redefinition of one of the base units of the international system of units. So just as we had to make a decision about what to do when the Earth's rotation was found not to be constant, and that decision was not very well made and had to be corrected a few years later. And when we had to change the definition of length from a meter bar to the wavelength of light, and today, where we're changing the definition of the kilogram from an artifact, a piece of platinum iridium, to defining Planck's constant, and you'll learn how that works later on this morning. We're now at a similar crossroads where we have to decide what to do about the second. We see that the old technology, the microwave clocks, are severely limited. We see these new technologies that are attracting us to change the definition of the second. But how are we going to choose? We have so many wonderful atoms. Different isotopes of strontium have different opportunities and different difficulties. Aluminum ions, ytterbium ions, neutral ytterbium, neutral magnesium, mercury ions. We have ions, neutrals, bosons, fermions. Each of these different kinds of atoms has their own advantages and disadvantages. And these advantages and disadvantages have to do with things like just simple convenience, the fundamental line width, the nature of the collisions, the nature of the black body shifts, the nature of the light shifts due to the light that are trapping the atoms or the light that are probing the atoms. The natural lifetime, well, that's the same as the line width. The rate of photon scattering in the lattice. All of these things can be different for each one of these atoms, and the question is, which one do we choose? And then there's the question of neutrals versus ions. Neutral atoms in a lattice, you can have lots and lots. You can have tens of thousands, maybe even hundreds of thousands of neutral atoms in a lattice. That gives you really good precision. This is why Junyi is able to get into the 19s with just 1 hour of observation time. On the other hand, ions are completely free of collisions, which is not the case with the neutral atoms. And the ions are showing the best accuracy, at least today. That may change tomorrow. And so this idea between ions and atoms, but at the PTB, Tanja Melstrauber is showing that maybe you can have a whole string of ions and make them work just as well as a single ion. And so you could then dream that maybe you could get 100 ions, quantum entangle them so that you can beat the shock noise limit, and then maybe 100 entangled ions could be as good as 10,000 unentangled neutral atoms. What to do? So we need to redefine the second with an optical transition. We're already using these transitions as de facto frequency standards. But what are we going to do for the redefinition? So here is my opinion on the subject. We need to pick one atom and one transition to define the SI second, and it's too early to do that because we simply don't know enough about the way in which all these wonderful candidates work when we have to work with them for years on a daily basis. And we haven't had enough cross-laboratory comparisons to make sure that we really understand what the accuracy of these clocks are. Because we can do all these calculations of how well we've understood the systematic errors, but until you compare two clocks, especially two clocks that have been made in different laboratories with different techniques, then you really start to understand whether you understand these systematic errors. So we're not ready to do it yet. And another thing I want to emphasize is there will never be a right time to do this. There will always be questions about what improvements might happen in the future. And eventually we will have to make a decision because we can't continue the present situation of having the definition of time not live up to what's possible in making the measurements. And the other point I want to make is that whatever we do, it's not going to be the end. Whenever we make a final choice, eventually new technology is going to emerge and is going to make that new definition obsolete. Here is one of the reasons. Nuclear transitions. People like Eckhard Pike and other people in laboratories around the world are trying to do laser spectroscopy of nuclear transitions. Okay, just think about that for a moment. That you shine a laser on an atom and change the state of its nucleus. And that nuclear transition will have a line width that makes it better than any of the optical candidates that we've been thinking about. And so we're almost certainly going to redefine the second as one of those electronic transitions in atoms, but this may come along and make that definition obsolete. We are not, at least not yet, able to use this beautiful definition of defining a fundamental constant. The obvious fundamental constant to define would be the Rydberg. But the technology for using the definition of the Rydberg to make an optical frequency standard doesn't yet exist. And it looks really, really hard. So we're not going to do that. We're going to define the second to be strontium or ytterbium or aluminum, and it's going to become obsolete. And so we aren't going to be able to use this beautiful definition to define time in the way that the new SI defines mass and length and electrical current and temperature. And so this is the set of defining constants that will become official on the 20th of May. This new SI really does achieve the revolutionary ideal of providing measurements that are good for all time, for all people, except for time itself. And again, this symposium coming up, but as for the future of time, well, only time will tell. Thank you very much.